Okay, good afternoon, everyone. So welcome back to the course. Today, we are start a new part of the course, part 4, hardware description language, Verilog. So, this set of lecture notes is adapted from notes from Professor Choi, again. So we are spent about 2 weeks in this part, maybe 1.5 weeks. Now here is the content for this part. First is the overview of Verilog, which we will cover today. Then Verilog variables, structural descriptions, behavioral descriptions. And finally, I present Verilog to construct final state machines. So for the overview of Verilog, Verilog is a type of hardware description language. So many people think that digital design is a straightforward, logical process. So you may start with the idea of what you need to build, and then you build it. And this sounds very straightforward, but real design is not like that. I think you have some experience. Firstly, you think you have an idea of what you need to build. This is some rough idea. Then through the design process, you figure out what you really want to build. You fine-tune the design. Along the way, you make the design. And it is important to validate the basic idea early in the design process. So what you build depends on the implementation capabilities and constraints. Often implementation problems will change the specification. So there is a need for a language, a hardware language, our description language that helps with the real design process, with the interact design process, and helps you to fine-tune your ideas throughout the project. So hardware description languages are used to describe designs, digital designs. And it is capable of describing designs at a very abstract level, even in the conceptualization phase of your idea. So this approach works at the level of functional blocks, not logic gates. Although it can describe logic gates, and it can be used to construct logic gates, but it's more useful for it to at the level of functional blocks. And the complexity of the functional blocks is up to the designer. And it can be very abstract in the beginning and be fit with more details along the design process. So a functional unit could be an ALU, arithmetic logic unit, could be a microprocessor, those are very high level descriptions, high level things. So the description consists of a list of function blocks and their interconnections. And for each functional block, we need some description. And the language needs to support hierarchical description. So a function can contain another functions inside, right? It's a nested of functions. And the hardware description language should support the verification of function description. That means the language description, the function specification can be executed, can be run. So the functional high-level specification can be checked. So you can run the language and check what it does. Like a programming language, you can run it and see what it does. And at very high levels, the design should be independent of the CMOS technologies used. And this can open synthesis opportunity. Once you describe a hardware behavior with a language, then and it can be synthesized into gate level. So HDL, hardware, there are several hardware description languages. The first one is Verilog. This is the one we are going to use in this course. Verilog is a simple C-like language. It has C-like syntax. For both structural and behavioral hardware constructs. And there are mature sets of commercial tools for synthesis and simulation. The second popular language, HDL, is VHDL. It stands for Very High Speed Integrated Circuit Hardware Description Language. It was created by the US Department of Defense, but it is open for the public, for the public domain. In syntax, it's very close to Verilog, but with more overhead in the syntax. So the VHDL is usually, the file is usually larger than Verilog. And there is a version of Verilog called a system Verilog. It enhances Verilog with strong typing along with other additional functions. And there are two new type of hardware description language nowadays becoming important. First new one is BlueSpec. It was invented at MIT, but it's protected. Its IP is protected, proprietary. you need to pay to use it. And you may obtain it from this link. Another new language getting popularity is Chisel. It's stands for constructing hardware in a scale embed language. It's open source. It developed at UC Berkeley, available at this link, Berkeley. And now there's CPU architecture called RISC-V, RISC-V, also from UC Berkeley. RISC-V, for many development, RISC-V uses its own hardware discrete language, Chisel. In terms of popularity, Verilog is the most popular. It's almost the hardware discrete language, default hardware discrete language used in Silicon Valley in India. And here is a brief history of Verilog HDL. It was introduced to the industry in 1985 by a company called Automate Integrated Design Systems. We named that Gateway Design Automation a year later, and finally acquired by Cadence Design Systems in 1989. As a Cadence, an important EDA vendor, Cadence, it now owns Verilog, but it is an open source one. Verilog was created as a simulation language. The name is like a verification of logic circuits, Verilog. For verification purpose in the beginning, and it was used in the synthesis context at a later stage. So once you can describe language, simulate it, then you can use it for synthesis. It was all open to the public in 1990. So Verilog is now recognized as a standard for everyone. It's free for everyone. And the official reference manual is specified in these documents. IEEE standard number 1364-2001, Verilog hardware discrete language. For system Verilog enhanced version. Another standard document. You can search for it. And there's a very thick document. You can take it as reference. As I said, Verilog is the language of choice, hardware discrete language of choice of Silicon Valley companies. Initially, because of its high quality tool support and its similarity to C language syntax. And VHDL is still popular within the US government and in Europe and Japan. Most major CAD frameworks now support both languages. And here we have a number of reference books for this course. Let's Verilog HDL by Samir, Verilog Designers Library by Bob. And this one, CMOS VLSI Design, Circuit and Systems Perspective. This is about digital circuits, but in the Appendix A, there are many good examples for Verilog. This is one of the important reference book for this course. And there are many useful websites providing Verilog documentations, including these three. Okay, now here is a quick look at Verilog. The Verilog description look like programming languages. like C, Pascal. In C, we have functions or procedures. And for each function, we have procedural parameters. Within a function or globally, we have variables. As in Verilog, we have similar things. For functions in C, the counterpart in Verilog is called module. Module, something like function, but not exactly the same. For functions parameters, and the counterparts in Verilog are ports, input and output ports. Variables in C, counterparts in Verilog are wires and registers, or wires. As variables like digital signal, you have wire, then you can be high or low, representing a logic variable. And registers can store and those logic variables. So these are similarity between C and Verilog. And the block structure is a key principle. So within a function, there can be other functions. So we can use hierarchy or modularity to manage the complexity. You can start with very abstract modules. And in each module, you can define the details, and then you can define details in the next level, so on and so forth. But Verilog are not normal programs. The module execution is concurrent. The C language, each line of code, those lines of code are executed sequentially from first line to second line, executed sequentially. But in Verilog, all the modules execute concurrently. It means every block has its own so-called program content. So it's not like a C language. It's a hardware thing, because hardware is like this. Hardware, they do not operate sequentially. If you have different blocks, they all execute at the same time. So modules are really communicating blocks that communicate with each other. And this simple example illustrates the Verilog view of the world. So a design consists of a set of modules, and these modules are capable of communicating with each other. That's Verilog's world view. They view the design as a collection of blocks, a collection of communicating blocks. And so to enter design, there are graphical methods. You can use graphic editor. There are graphic editors, but we will not use them in this course. Instead, we will use the text method, like Spice. You type in descriptions. You label the wires, label the modules. And so for example, this Y labeled as B, C, A, bus, which is a collection of multiple wires, D. So you label wires and use them as parameters in the module calls. So module. A module is a basic building block in Verilog. So a module is a block of hardware with inputs and outputs. The syntax of Verilog module looks like this. You start with the keyword module, a fixed keyword module. That's the first line. Module, then followed by the name of the module. You name this module. After the name of the module, you have a module terminal list. That's input and output wire names. You have a list of wires inside this pair of brackets after the module name. Then after this terminal list, there's a semicolon here. Then you start the description of the hardware within this module. Some module in there. And at the end, you need to type this keyword and module. That's to indicate that this segment of code describes such a name, such a module. And a module can have hierarchy. It can contain instances of other modules. So let's make the hierarchical approach possible. And for this terminals, we also call them as ports, modules ports. There are input ports and output ports. So the ports associated with a module are first listed in the module declaration. First listed here. Then their types, either input or output or in are declared in separate statements, usually immediately after. Immediately after this first line, you declare which terminal, which port is which type. So there are three types for the ports: input ports, output ports, or bidirectional ports. Input port is have a keyword input. Output port, keyword output. Bidirectional keyword IO. So often for Verilog, the keyword starts first. Yeah, for a module, when you design module, the keyword module starts first. Even when you call a module, the keyword starts first. To let you have a feeling, here is an example. This is a design. At the top level, we have a module called system. It includes everything. So there's no I/O. So it is a collection of some modules, some blocks. So here it has a clock generation block, or clock generation module, a pattern source module, controller module, data path module. For example, to declare a clock generation module, we start with a line like this. Clock generation, that's the name of the module. I mean, it's the name of the module, not the name of the instance. Because you can place several clock generation modules in the design. So this starting word is the keyword. And it follows by the instant name of the module. This instant, we just call it clock gen. It can be the same, clock gen. It has two ports. Say phi 1, phi 2 generates two clock phases. Say controller. First, this is the keyword controller. This is a module defined somewhere else in some other part of the code. And this instance is named as controller 1. Okay. And followed by a list of IOs. And that is phi 1, phi 2 other wires. So, and this is a list of IOs. Because you named these wires, then just put them together. You know how they are collected. You know how these blocks are connected to each other. So for a module, the syntax to call invoke a module is like this. First, module name, that's the keyword you defined, an instance name, followed by a list of wires. So in this example, the instance name and the module name are the same except for all the controller 1. Now here is a reverse to the design domains. Remember that we can view the designs in 3 domains, either behavioral, structural, or physical. And in each domain, you can divide them into different layers. And so so Verilog can describe a design in both behavioral domain and structural domain. So Verilog is both a behavioral language and a structural language. So in fact, a module can be described in Verilog in different abstraction levels and domains. It can be in behavioral, so-called data flow. We'll get to it soon. Gate level, switch level. The gate level and switch level, they are both structural description. Well, switch level is one level lower. For example, here, say I have an ADA example. I can describe it using Verilog in the gate level. So I define a module called ADA. Module name is ADA. It has 4 terminals, 4 I/O ports, some carrier A and B. So that's the first line to define the module. Then after this first line, I declare the input or output for the type of each port. Say I declare the sum and carrier to be output ports. And A and B are input ports. So I start with a keyword input, A and B, semicolon. And this looks like a C language. Now after this port declaration of this 2 lines to construct this adder. This is 1 bit adder. The circuit is like this. So I just described a hardware connection like this. Exclusive all gate. gives the some output. Then see the here we are. This is a half adder, 1 bit half adder. So now this line declares the OK. Say there is a OK. And the OK's name is called G1. The instant name, I give it the name G1. Call it G1. It has this G1 is defined somewhere else. It's an OK. Actually, standard OK is provided in a library, in any library. So it's output sum. So the first wire is the output wire, output port, and then the two inputs. This number here, this hash symbol followed by a number here, indicates the delay of this gate from input to output. I can declare as a delay, and the delay is 5 time unit. This delay number is an integer. There is no absolute value for the time delay. It's just a abstract delay, abstract time units. It's 1 unit, 2 units, or 3 units. There are 5 abstract time units of delay. So that's delay. And then similarly, we have an AND gate. Instem is G2. It accepts input A and B and produce an output at this terminal, at this one, and AND module. So this is a AND gate description using Verilog. And this description is obviously in the gate level description. We describe every gate and the link connections in this module. So this is a structural description. The structure is like this, down to the gate level. It's very detailed. So you see that Verilog can describe hardware in this way. It's just like SPICE. So if it is just like the SPICE, it is not very useful because you need to construct every gate. Let me see. Gate level. Okay, so this is gate level. Well, the Verilog supports mixing abstraction levels and domains in a description. So we'll see that we have seen a structural description. This is one way to describe a design. The function of piece of hardware. It provides components wiring. I use the structure of the units to define its function, the connections, components, primitives. Yeah. And basically, this is what we did in the example on the previous slide. But if we did this all the way down to logic gate or switches from high level, so you would have just created a text-based schematic entry system. And this is not a very good idea because you need to make a design for everything manually. Type in the design manually. Although it is hierarchical, you can save some time. But there is no automation of design. Everything is from your mind. The structure is from your mind. So not very helpful. So we need another method to specify function of a block, even at the bottommost level. Verilog provides so-called declarative and procedural methods to describe function. Basically, these two methods are behavioral descriptions. Declarative description is also called a data flow description. It provides logical relations between inputs and outputs. It's a mathematical function. Just give it a mathematical function, mathematical behavior between variables. Assign outputs to some combinational logic. It's not like this conventional hardware. So it models a piece of combination logic for combinational logic, not sequential. We use a CLAC expression syntax. And this declarative or data flow description is denoted by the keyword assign. Now here is the same example, same ADA, same function, ADA, but now I use declarative description. The module definition input output are the same as before, but here only these two lines are different from the previous one. Instead of specifying combination of gates, here I just declare that this output sum, this variable, this while sum must be equal to A exclusive of B. And this is a symbol of exclusive of A. I declare it sum equals to A exclusive of B. Then the output will be produced with certain delay, hash 5 units, 5 time units. And carrier must be equal to A and B. This is one bit and symbol. I declare carrier should be this. I don't specify the implementation. I just declare it like this. Declare the function is this. The keyword is assign. Just assign. So basically A and B result is assigned to the carrier. A exclusive of B is assigned to the sum. That's the meaning of assign. So so the outputs of in a assign statement are whiles. Whiles, not registers, are whiles. I will talk about variables later. But in general, there are two types, whiles and registers. But this whiles can be a single bit or multiple bits. Okay, now you see the second description method for the same function in Verilog. This is declarative or data flow description. Just assign some value to the output. Another way to describe a function is called procedural description, or named behavioral description. Actually, data flow, the previous one, can also be regarded as behavioral. But now here the name is procedural or procedural description. It uses the keyword always to provide the functionality using a tiny program, not executes sequentially. This is like traditional program. Executes line by line, line after line. And inside an always block, it's called always block, you can use standard control flow statements like if, then, for loop, cases, while loop. And statements can be compound You just need to use begin and end to form a block. Now here is example for the adder, same function, adder. So a module, I define a module adder with 4 ports, some carrier A and B. A and B are inputs, some carrier outputs. Now, for user variable, I need to this time need to declare the sum and carrier as a register variable. We'll go into the details later. Anyway, the sum and carrier variables. Now I start with a procedural line-by-line statement. Procedural description. The keyword is always. Always at this event, we'll execute this block of code. Always. So once you have this event, add something. Always add something. So A or B here means once you have a change in A or a change in B, an event is a change of a signal here. If a signal stays unchanged, there is no event. If a signal changes, it's stay from 1 to 0, 0 to 1. There is a change. When there's an event in A or B, do the following. That's procedural description. What is here for this adder? Not like usual programming language. Say, I check the input. Say if input A has a value of 1, A, and B has a value of 1, and A equal to this identical, two equal signs to compare A and B. If you compare A and 1, A and 1, this is true, then this small statement will give a true output 1. If this and this are valid, then do the following. You let carrier equal to 1 after 5 units of delay. Now be careful here. We also have things like carrier equal to something, but we don't have an assign statement. We don't have an assign statement before. The keyword assign previously checked here. You have assign. That's the keyword for data flow. But here you just for now you just pay attention to this. Within always you don't here you don't have the assign keyword. But here you pass this 1 value. Under this condition, you pass 1 into the carrier output after 5 unit delay. You may put a sum here. Else, you pass a 0 to the carrier output. So this is like a traditional C program. You execute line by line using if statement for statement, or most common is case statement. So by this, you can also realize a adder, 1-bit adder to the so this is very low level. It's just a unit. Okay, so that's the behavioral or procedural description. Procedure starts with always. So now we have 3 methods. One is structural, one is data flow or declarative, then this procedural description for the same function. Yeah, I think I will stop it here for today. So any questions? If no, I'll see you tomorrow.